Okay, so these are the topics I have been asked to teach by you people. So I'll try my best to cover all of this today, hopefully in a couple of hours. If not, I'll finish as much as I can today, and the rest I'll take another session tomorrow. So the topics are GMM, SVM, SVR, regularization and optimization, LDA and FLT. So we'll start with GMM. Before I go into GMM, your machine learning models can be broadly classified into two types, generative and discriminative models. So generative models, they learn the distribution of your underlying data. Discriminative models, they just learn the boundary or the line of separation. So I'll explain it with this image here. So we have, let's say, two classes or two categories of items. Class A, which is your green color data points, and class B, which is your pink color. So these data points, they have two features or two attributes, let's say F1, F2. So I plotted a graph with F1 along one axis, F2 along another axis, and I've plotted these data points. And it turns out that the green data points or the class A data points lie somewhere here, and the pink points or class B points lie here. Now, if I want a model to perform classification, so when I give it a new data point in, let's say, this orange point, which I'll call X, orange or red, whatever, I want this point to classify whether it belongs to class, I want this model to classify whether it belongs to class A or class B. There are two different approaches to this problem. One is a generative approach, the other is a discriminative approach. So what a discriminative model will do is it will just learn the equation for this blue line here, the line which separates your class A from class B. So it will try to learn what is this line, and then when I give it a point X, it will figure out whether the point lies on this side or this side of the line. So if it lies above the line, your model will classify X as belonging to class B. If it lies below the line, it will classify X as belonging to category A. So it is only going to learn the line of separation and do classification based on that. It doesn't really care about the properties of your class A items or the properties of your class B items. That is a discriminative model. Your generative models, on the other hand, they are interested exactly in these properties. They try to learn the distribution from which your class A comes, the mean, the variance, the standard deviation of your class A items. Similarly, the mean, variance, standard deviation of your class B items. And based on that, it will check whether this point is more likely to have come from A distribution or from B distribution. That is a generative model. So we're going to look at GMM and SVM, where GMM is generative and SVM is discriminative. So we're going to look at both these concepts today. So is the difference between generative and discriminative clear to everyone? I
Yes.
assume there are no
Yes.
questions. Right. So the first thing we will look at is GMM. It is a generative model, meaning it is going to learn the properties of your underlying data distribution. So because it learns the properties, it can be used to generate new data points or new samples from that distribution, which is why we call it a generative model. But in our case, we are going to be using
Okay.
it. Sorry, someone say something. Did anyone have a question?
The generative model, it doesn't care about the boundary, right?
No, it doesn't care about the boundary. It just learns the properties of distribution A and the properties of distribution B. So now when I give it a point X, it will check what is the probability that X would have come from A. What's the probability that X would have come from B? Whichever is the greater of the two, it will classify your X as belonging to that category. That's how generative models work.
Okay.
So the reason they are called generative, first of all, is because it is learning the properties of this distribution. It can now be used to generate new samples which come from this distribution. So when it takes these data points from class A, it's going to learn the mean of A and let's say the variance of A. Now, using this, it can generate a point, let's say x2 or x3, sorry, x2 or x3, which is likely to have come from this distribution. So you use generative models generally to generate new samples, but here we can also use it for classification. That's what we're going to do with GMM, right? So it models a Gaussian distribution for every class Y. So here we have two classes, right? We have a class A and a class B. So what your GMM does is it assumes there are two Gaussian distributions, one which I will call A, the other which I will call B. Each corresponds to one of your class labels or categories. Now this distribution has mean mu A and covariance matrix sigma A. This has mean mu B and covariance matrix sigma B. So it will assume that these two distributions exist, and all my green color points came from this distribution. All my pink color points came from this distribution. Now I have a new point, an orange color point. I want to figure out whether it came from this distribution or this one. So what it will do is it will compute probability of A given X. I'm assuming my new point is X. So probability of A given X is the probability that the data point X belongs to class A. Similarly, probability of B given X is the probability that my data point X belongs to class B. So it will compute these two and it will choose whichever class has the maximum probability. So let's say this is a 0.65 and this is a 0.35. Then your GMM will classify your point X as belonging to class A. So this is the broad idea of how GMM works. So now we have two questions left to be answered. How does it find out these values, mu A, sigma A, mu B, sigma B? And how does it find out A given X, B given X? This is what the main math behind GMM is, which we will be looking at now. But is the broad idea of how GMM works clear to everyone? I assume there are no questions. So we will go on. So first we'll see how to compute this probability of class given data point, right? This is what we refer to as probability of y given x. Y is your class label, x is your data point. So P of y given x is basically probability that data point x comes from, sorry, comes from something, came from class y. So that is your probability of y given x. Now, if you remember Bayes' theorem, this can be expanded as p of x given y into p of y divided by p of x. So given that I'm taking a sample from class y, what is the probability that the sample I'm taking is going to be x into what is the probability that I get a class y, first of all, divided by what's the probability of getting data point x. So this is the expansion for this expression. Now this denominator term is usually a constant because p of x is probability of getting that data point, and the data point is given to you in the data set. So this is like one, you're definitely going to have the data point because it's a given. So you can ignore the denominator term. All we are concerned about are the two terms in the numerator, x given y and p of y. Now P of y is very straightforward to compute. You just go to your data set, you see how many objects of class y divided by total number of objects. So let's say if you have a bag containing 6 blue marbles and 5 green marbles, then your P of B is just going to be 6 upon 6 plus 5. This is how you compute your P of y. This is very straightforward. Now, how do we compute P of x given y? So we assumed that your classes follow a Gaussian distribution, right? A has a specific Gaussian, B has a specific Gaussian. Now, what is the probability of getting a particular element sampled from a Gaussian is exactly what is described by the probability density function of the Gaussian. So P of x given y is computed using this expression if you have a univariate Gaussian, and this expression if you have a multivariate Gaussian. These are the PDFs of univariate and multivariate Gaussian respectively. Right. So let me quickly summarize what I said so far. GMM is a generative model. It assumes a Gaussian distribution for every class. It learns probability of class given data point. Then for whichever class this term is maximum, it classifies your data point as belonging to that class. Now this can be expressed as probability of data given class into probability of class divided by probability of data. This is a constant, you can ignore this. This part you will simply get it from your data set, how many elements of this type divided by total number of elements. For this, you use the Gaussian distribution PDF, the expression for which I just showed you on the next page. Right? So are we clear so far?
Yes.
Right.
Yes,
Now,
Nata.
yeah. Now this is where we run into a challenge. So if you want to be able to compute this expression, you need to know mu and sigma. Right. So when I told you it models two Gaussians, I said for every Gaussian it has a mu A and a sigma A. So similarly a mu B and a sigma B, right? So we need to know the mean and covariance in order to be able to find P of X given Y. Okay, let's try to find the mean and covariance. So for this, I'm sure in your statistical inference, you would have learned something called the maximum likelihood estimation method, right? So where you try to maximize the joint probability. So the joint probability is given by this expression, probability of x1 given particular class into x2 given a class into so on, so on. And we, because this is a product, we convert this to the log. So we try to maximize the log likelihood. But ultimately, it is these quantities overall which we are trying to maximize, right? So you see what the problem here is. To compute P of X given Y, I need sigma and mu. And to compute sigma and u by maximum likelihood estimation method, again I need P of X given Y. So we are in a sort of deadlock situation. Uh, do you guys understand this? Do you want me to repeat?
Understood, sir.
Right. So the conclusion here is that maximum likelihood estimation directly will not help because we are kind of stuck. So we need to do something, and that something is what is your EM algorithm. So EM stands for expectation maximization algorithm, right? So this is a very simple algorithm. It is basically your maximum likelihood estimation, but one extra step before that. So I'll tell you. So initially we are just starting with random mu sigma values, and you're finding the log likelihood. Now what we do is, before going for your maximum likelihood estimation, we are computing something called the responsibility. This responsibility, which is denoted gamma of x, is given by some pi k into normal distribution PDF. This n of x given mu sigma is nothing but your Gaussian PDF, the big expression which I showed you on the previous page. For so this responsibility term for a particular class for a particular data point is defined as pi k is some weight for that class into Gaussian PDF for that point for that class divided by weight into Gaussian PDF for that point for all classes. Let me repeat this. What we're doing in the EM algorithm is we start with random initializations of mu sigma and some weights pi k. I'll tell you what these weights are in a minute. So we first compute the responsibility term denoted gamma k of x for data point x and class k. It is given by weight for that class into normal distribution PDF value for that class for that data point divided by summation across all classes weight of that class into normal distribution PDF for that class for that data point. So it's like probability of this class this data point belonging to this class divided by the weighted sum across all classes. You can think of it like that. This denominator is like a weighted sum. So this term is what we call the responsibility. So now I'll talk about what is this pi j. I'll talk about what is this responsibility, and then we'll proceed to the next step. So pi j is very simple. It is just weights which you assign for different classes in your data set. So that if your data set has a class imbalance, your model's learning is not going to be affected by it. So for example, let's say you have a data set where you have 90 samples of class A and only 10 samples of class B. So you train a model using this data set. It is highly likely that whatever input you get, your model will classify it as A because it has more learning of this type. So in such cases, you can set weights like 0.1 for this probably and 0.8 or 0.9 for this, which means your class B also finally gets enough weightage so that the learning is not biased. So just for that purpose, we have this pi k term. If your data set is balanced, you can set all weights equal to 1. No problem. So that's a very simple thing. Now, what is this whole responsibility term? What's the idea of this? So the responsibility is something like probability of z given x, where z is what we call the latent variable or hidden variable. It is a substitute for P of y given x. Now, let me remind you of why we came to EM in the first place. I want P of x given y. For that, I want mu and sigma. And for mu and sigma, in turn, again, I want P of x given y, right? So, sorry, this must be P of x given. So it was a deadlock situation. So here we are introducing a latent variable z, and this responsibility term is going to be something like a substitute for your p of x given y. It is like, you could say something like an expected value of p of x given y, which we use to get mu and sigma, right? So instead of, we need this for this and this for this. So at some point we need to break the cycle, right? If we want to make any progress. So instead of this actual thing, I'm using this gamma, which is like a dummy or a substitute in place of this. Using this, I'll get mu and sigma, and then using this, I'll get p of x given y. Using this, I'll get p of y given x, and then my GMM will do the classification. This is the idea. So this is why we compute these responsibility terms. Once that is done, you have everything which you need to do the maximum likelihood estimation. These steps are just your normal MLE estimate. You set the log likelihood equal to 0. You get your expression. From that, you will get your mu and sigma. This is how the EM algorithm works. So now once you have mu and sigma, we can compute P of y given x, and then you choose whichever class gets the maximum probability. Your classification is done. This is how your GMM works. So any questions? I assume there are no questions. Shall we move on to SVM?
Yes, sir.
Okay. So the next thing we're going to see, the next model is support vector machine. This again is a classification algorithm. This one is discriminative, meaning it only wants to learn the line of separation between your two classes. It doesn't care about the distribution. But line of separation, it wants to learn the best line of separation. So I'll first go to the picture, I'll explain this, and then we'll come back to the text. So here, this is one class, class 1, which is triangles, and class 2, which is circles. And you can see that this is a fairly good enough line of separation. It separates the two classes. You don't find any triangles on this side. You don't find any circles on this side. This line again is also doing the same job. Again, there are no misclassified points. So for any given, a couple of classes and your data points are plotted on a two-dimensional space like this, you can have multiple possible lines of separation. So how do I decide which is the best line of separation? That's my first question. So now let's say I have a point over here, a point X. Now this point could actually be a triangle. It is rather close to this triangle. But just because it falls below this line, X will be misclassified as a circle. Or I could have a point over here. It's rather close to your circles than to the triangles in general. It could be a circle, but just because it lies above the line, it could be misclassified as a triangle, right? So with this line of separation, we see that there is quite some probability of misclassification. Whereas if you take this line, the chances of such a misclassification happening are less, because the distance, perpendicular distance between your line and the closest point on either side is maximized. I'll repeat, the perpendicular distance between your line of separation and the closest point on either side, this distance needs to be maximized. That is when we call it the best possible line of separation. The best line of separation is the line which maximizes the margin. Margin being the perpendicular distance between the line and the closest point on either side. So what's the idea of SVM? Given these data points in this two-dimensional space, find the best possible line, the line which maximizes the margin. This is what we're going to try to do. So is the idea clear to everyone before we go to the math?
Yes.
Okay. So, okay, we'll go into the math now. So yeah, so essentially it's a straight line. We're assuming it's a straight line, right? So if you remember from your linear expression, sorry, linear regression, W transpose X plus W naught is your expression for a straight line. That is, these are the weights. This is an additional bias kind of a term. This is going to be your data point, and this is what your predicted value, right? So if your W transpose X plus W naught is greater than or equal to some value delta, so this, if this distance, if I'm going to call this delta, if my predicted position of the point W transpose X plus W naught is greater than plus delta, then I'm going to call it class 1 or the positive class, in which case I'll give it the class label as 1. Di is just my term for, it's a label corresponding to class. So if it's class triangle, I'm going to give it, Di is going to be 1. If it's class circle, Di is going to be -1, right? So similarly, if W transpose Xi plus W naught is less than equal to minus delta. So this distance along the positive direction, I'm calling it plus delta. This distance along the negative direction, so I'm calling it minus delta. So if it is along this side, the class label is going to be a -1. If it's along this side, the class label is going to be a 1. That is what this expression is saying, right? Okay. So arbitrarily, you can set delta equal to 1. You can set it to be any value. For the sake of simplicity, we're setting delta equal to 1. So what this makes it is W transpose Xi plus W naught greater than equal to 1. Then my class label is going to be a 1. If it's less than -1, then my class label becomes a -1. Now, if you combine both of this into a single expression, this is what you will get. So I will encourage you to try this out for both cases. Like after this class is over, take a minute to check if for this case, this condition is satisfied or not. And for this case, you will find that both of them are satisfied, and it's just very simple math. So I'm not going to spend too much time on that. So ultimately, based on our classification criteria, when I say if the points lie above this, it's a class 1, and if the points lie below this, it's a class -1. When I say that, ultimately, by combining both of those conditions, we get this constraint, right? So we have a constraint. And the second thing we want to do is maximize the margin. Now, there is a lot of linear algebra, a lot of math behind this, which is beyond the scope of our course. So I'm not going to explain all the linear algebra to you right now because it's not necessary. I will ask you to trust me on this when I say this distance is 1 by norm W and this distance is also 1 by norm W, the modulus of that distance, leaving the plus minus the direction part aside. Just assume that I am choosing to call this distance 1 upon W and this distance 1 upon W. Now I want to maximize this distance, right? So the idea is we want to maximize W. So for ease in calculation, I'm going to make it maximizing half of W square. So the only reason I'm changing W to W square and putting a half here is when the actual maximization happens, we'll be taking some derivatives here and some stuff. So it will become 2 upon 2 norm of W power 1. So this cancellation. So it becomes easy in calculation. So that's the basic idea. So what I want you to take away from this whole slide so far is that we want to maximize norm of W. That's our objective function. And we have a constraint, right? That's the idea. So we have a constrained optimization problem. We had a constraint which said di into W transpose xi plus W naught minus 1 greater than 0 or something. And this is maximize half of norm W squared. So you have an objective function and you have some constraints. Then the technique you use to solve the optimization problem is something called a Lagrangian technique. So are we clear so far before I proceed? Any questions?
If you maximize the W, the boundary there, the margin is 1 by W, right? They're like a little up
Oh,
here,
sorry,
right?
sorry, my bad. Yeah, okay, I am 1 second. Sorry, this is supposed to be W, my bad, my bad. Okay, the picture is wrong. I'm sorry, I didn't look at it before I picked it up from the source. Right. So again, there is a bit of linear algebra behind this, but your final objective will be to minimize 2 by W or to maximize W. Right. That's the thing. I'm sorry, the picture was wrong. Okay.
Okay, so that margin is W then.
Twice of W. You have one on this
Okay,
side and
yeah,
one.
2W. Okay.
Yeah. So which is what you want to maximize. Right.
Yeah.
Okay, so you want to maximize W, which is the same, which is your objective function, and you have a constraint over here. So we have a constraint optimization problem. So we go for the Lagrangian technique. So again, the Lagrangian technique is beyond the scope of this course. We're not going to look at the math. We'll just see the preliminary requirement for a Lagrangian technique, and then we'll move directly to the solution we get. We'll assume uh, there is a black box which has solved the Lagrangian for us, right? So for your Lagrangian, you first have to express your objective function and constraint in a specific format known as the primal form. Again, I do not know what exactly the primal form means because it's beyond the scope of this course. I will ask you to trust me when I say this is the primal form for this problem. This is our objective function. This part is our constraint. And this lambda I, these are our Lagrangian coefficients. So this is what is going to be your output from solving this method basically. Right, so you'll get a bunch of coefficients when you solve this Lagrangian. So we are supposed to express our question in this format. And when we do it for our specific case, this is the expression we get. Now, once the Lagrangian is solved, the final expression you get for W is this, and for W naught, it is this. This is what we wanted, right? We wanted the line, which is W transpose X plus W naught. So you have W and you have W naught here. And you will get these Lagrangian coefficients. Now, this gives you the line, and the Lagrangian coefficients give you the support vector. So if you remember, this method is called support vector machine, right? So what are these support vectors exactly? Is the points which have a non-zero Lagrangian coefficient are called support vectors. So I'll go back to that graph I drew. Oh yeah, okay. I'll go back. I'll take this picture. Now, we decided that the line on the right side picture was the best line, right? So to decide that best line, we considered this point and this point. We maximized the margin and we said this is the best line. So these points are the support vectors for this case. So support vectors are basically those points which help you to identify the decision boundary. So for these points, your Lagrangian coefficient will be non-zero. For all other points, it will be 0. And generally, when you take a typical large enough data set, the example we saw, we had barely a handful of points. When you take a big enough data set, you will have very few, some probably 10, 15 points which have a non-zero lambda coefficient, meaning only 10, 15 support vectors. And for all other points, your Lagrangian coefficients are going to be 0. Right? So these points on either side help you to decide the best boundary, the boundary that maximizes margin. And based on that boundary, your classification is going to happen. And that boundary is given by your W and W naught matrices. So this is how your SVM works. Is that clear?
Yes.
So moving on, soft margin SVM is just a small variant of SVM where there's a small what do I say, a modification where it allows for something called slack variables to permit some misclassification. So it is possible that one or two exceptions may be there, right? So one of these points could be on this side of the line, one of these points could be on the other side of the line. So just because there are one or two exceptions, you don't want to think the best line you selected is actually a wrong line. So for that, we introduce some slack variables eta I. So they sort of create a penalty for misclassification. So this still remains your best line of separation. But if a few points are of this type are on that side or of that type are on this side, there's a small penalty induced for that, which makes sure when your model is classifying a new point, it classifies correctly. That's the whole idea. So there is not much of a change here. The only thing is in your constraint, last time I think we had di into W transpose xi plus W naught minus 1 greater than equal to 0. This was your constraint. Here it will be the whole thing minus 1 plus eta greater than equal to 0. This extra slack variable will be added. So in your Lagrangian primal form also, at this point you will get a plus eta over here. That is the only change in your soft margin SVM. There are no other changes. So is SVM clear to everyone? Shall we move to support vector regression? Okay, I assume there are no questions. So support vector regression, as the name suggests, is an extension of the SVM concept to regression. So you have a bunch of data points. Again, you want to fit a line. This time it need not necessarily be a straight line. It can be a curve like this also. And this curve, using this curve, you want to perform regression, which is given a new data point. You want to predict the value of y for that point using this curve. Now the thing here is, because we are using support vectors, which are points not exactly on the line, but some distance away from the line on either side, which is the whole idea of support vectors, right? So we define something called an epsilon tube around this line. So what happens is, in regression of any sort, you have your x, your original value y, and your predicted value y cap. And you have some sort of an error function, which is like y minus y cap or y minus y cap whole squared something, right? So in support vector regression, let's say your original y value is somewhere here and the predicted value is this. If it lies within plus or minus epsilon distance, then we consider this error as 0. Only if your predicted value lies outside this epsilon distance, we take that error. So we are giving your model a little bit of leeway basically. So this is my original line, but I'm giving you this much space on either side of the line. You are allowed to predict wrongly within this much distance on either side without being penalized. Only if your prediction exceeds that boundary, I will give you a loss function and you will have to modify your weights. That's what we are saying. Because our tube is going to be defined by support vectors. The whole idea of support vector regression is using the support vector. So your error will be 0 if your original minus predicted lies within some epsilon boundary. Otherwise, it's going to be original minus predicted minus that epsilon boundary. So it's going to be this whole thing minus this thing. So this part will be taken as the error function. So this is how we define the error function. And again, half w square is your objective function. And this is going, I'll take another.
Can you tell the SVR thing around from first occur? I was not able to
Okay.
understand.
Okay, now, okay, wait, one second, I'll take a new page. Right, so, okay, we'll start with a little bit of basics. The concept of regression is you have a bunch of data points. You want to fit some curve to these data points. Am I right? So you have your original data point X, the corresponding Y variable, which is the answer, and your predicted Y cap. Now, let's say you fit, your points are like this, and this pink line is the line you have fit. What will your error function be? It's going to be some Y minus Y cap whole squared, or absolute value of Y minus Y cap, something like that, right? Now, this is the same idea I'm going to do with support vector regression. I have a bunch of points. I'm going to try and fit a line, but I am defining a tube of width epsilon around that line. So if this is Y, this is going to be Y plus epsilon. This is going to be Y minus epsilon. So what I'm telling my model is, I want, you are free to predict a value which is anywhere within this range. It doesn't, so if there is a point X, I'm sorry. So what regression does is you give it a point X, it's going to, using this line, it's going to predict the value Y corresponding to that point, which will be on this pink line, right? So now in support vector regression, it can be somewhere here, somewhere here, somewhere here, somewhere here. It can be anywhere within this tube, anywhere within a plus or minus epsilon distance of Y. So we are giving it a little bit of freedom. You find a line, but your actual prediction can be somewhere above or below that line. It doesn't have to be exactly on the line. If your prediction is within epsilon distance of the actual value, I will take it as a correct prediction. So it is like, let's say you're writing a numerical answer type question. The right answer is 0.6. You find these tests where they say any answer in the range of 0.5 to 0.7 is accepted, or 0.55 to 0.65. Anything in this range is accepted, right? They don't just give you a single specific value sometimes. So this is like that. So I've given you a point X. By regression, you're going to predict the value. The actual value is 0.6, but I'm telling you anything between 0.6 minus epsilon and 0.6 plus epsilon, I will accept as correct without any loss function. But if your value goes above that or below this, then I'll say your value is not correct. There is some error. You have to compute the error. You have to do your back prop or gradient descent, whatever, and you have to update your weights. This is the idea of support vector regression. So that is how your error function is defined. If your actual minus predicted is within epsilon distance, then the error is 0. Otherwise, there is some error, right? So again, this is your constraint. This is your objective function. This is a constraint optimization problem. So we'll go for Lagrangian. And when you solve the Lagrangian, this is the final expression you will get. So these are going to
Can
be
you
your
show those numerical parts so that I can take down some writing notes? Can you
I
show that?
okay, I will be sending these notes after the
Okay,
class
then
is
fine.
done.
Okay,
Like
fine.
as soon as the class is done, I'll make a PDF of this and I'll share it with
Okay.
you. Okay, so yeah, these are going to be your Lagrangian coefficients. This is your data points. Uh, this is just some constant weights, and this is your bias. And this is the prediction you are making for the new data point X. So that's the idea of SVR. Is that clear for everyone?
We use this Lagrangian thingy because of that same problem that we had in the
Because it's a constrained optimization problem. When you have an optimization problem subject to certain constraints, we use Lagrangian technique.
yeah. And the deadlock occurred, no? That thing is
No,
like-
deadlock was GMM, no.
Yeah, that is not here, no? Okay.
No, deadlock was GMM. For that, we used EM. That was a separate concept.
Okay, okay, I got
SVM
confused.
is right. So, any questions so far? If there are no questions, I think the next thing I wanted to do was, yeah, so we have completed GMM, SVM, SVR, optimization, regularization, LDA, Fisher's gradient distribution. Okay, so we go here, stop sharing. Okay, so I will move on to the next set of topics. I think I'll do. Okay. Are you able to see the PPT, Rudrashis PPT? Is it visible?
Yes, Akka.
Right. Okay. So we're going to look at Fisher's linear discriminant and linear discriminant analysis. Some of you wanted me to teach that. So it's actually very closely related to your GMM. So I'll finish that off. Then we'll, if time permits, we'll look at optimization, regularization, and we'll wind up, right? So the first thing I think I will start with Fisher's discriminant, and then we'll come back to linear discriminant analysis, right? So we're going to see something called the Fisher discriminant analysis. So before we go to LDA, so this is a very simple thing. There is not much to this. The only idea is you have some data points plotted along your XY graph. You want to find a projection direction or a line of separation. Projection direction is basically like your boundary, which we saw in SVM and all that, right? So you want to find that line or that boundary such that the separation between classes is maximized and the separation within classes is very minimized. So if you, maybe I will take a minute to draw and show this. Let's go back to this screen. So the idea is, so Fisher's discriminant analysis. So you have, this is your bunch of points over here, and this is your other bunch of points. I want to find a line of separation. Now there can again be multiple lines of separation. This is one possible line. It's another color, yellow, brown. This is one possible line. Multiple lines of separation exist, right? So I want to find a line such that all the points belonging to one class are clustered close to each other. They all lie close to each other, and the distance across classes is maximized. That is the idea of Fisher discriminant analysis. So it is basically the high level objective of what you're doing in your SVM also. SVM is one specific way of attaining that objective. Your Fisher's discriminant analysis is going to be a broad sort of a generalized way of looking at the same thing. And LDA is also going to be very similar. So I will now go back to the slides. Unit to share. Right. So the different classes are far apart from each other. Points within the class are tightly clustered. So how I'm going to do that is, we are going to define two terms. The within class scatter, SW, is defined as summation across all classes, across all data points belonging to that class, point minus mean of that class into its transpose. So basically this is something like your x minus mu whole square summed up over all your classes. So it is something very similar to your variance for every specific class, right? So what we want ideally is, if your class, if all the elements of the same class are like close together, then the variance within that class is going to be very small. If all the elements of a single class are pretty scattered around, if you find green elements throughout the graph instead of in like one corner, then your SW is going to be large. SW is basically the variance within one particular class. Similarly, SB is the between class scatter, which is going to be the variance between one class and another. So if your SB is very large, it means the distance between your green class and blue class is very high. They are well separated. If your SB is a pretty small number, it means there are some green elements, some blue elements, all of them are put together, pretty mixed up. So these are the two terms we have defined so far. We're going to be using these terms to come up with an expression that will help us find the best direction of projection. So any questions so far?
What's NK? N is the number of.
Weights, just weights for each class based on class imbalance.
Okay.
K represents each class. Right. Now the Fisher's criterion is this is your objective function. You want to find a line of separation. The line is given by Wx plus some bias B. We can assume the bias is 0. So ultimately it is the W or the slope weight matrix which I want to find. So you want to find a W matrix such that your objective function is W transpose SBW divided by W transpose SWW. SB and SW being your between class scatter and within class scatter respectively. So the idea is I want to maximize the numerator term and minimize the denominator term, right? Between classes, I want a lot of distance. I want my classes to be well separated. Within the class, I want the distance to be very minimal. So this is my objective function. This is something I am basically trying to maximize. That's the idea. So the overall idea of Fisher's linear discriminant is you want to maximize the distance between distance across classes divided by the spread within a class. Now, one way of doing that is going to be your LDA. So Fisher's discriminant analysis, basically it gives you the criterion or the objective function, which is I want to find the line of separation or the weights such that this particular quantity is maximized. Now, how exactly to go about that is what we'll see in linear discriminant analysis. So is FDA clear to everyone? I assume everyone's comfortable with FDA. So now, sure. Sorry, my bad, 51. Okay, so now we saw the problem statement, which is I want to find a line such that something is maximized, something is minimized, so on and so forth. So one way of doing that is going to be linear discriminant analysis, right? So linear discriminant analysis is very similar to your classification by GMM. In fact, I would say your the GMM based classification which we studied is a special case of your linear discriminant analysis, right? So what happens here is two approaches you have: generative, discriminative. We have seen this. Now LDA is a discriminative model, if I am not wrong. Yeah, sorry, LDA is a generative model. Sorry, my bad. So what this does is, yeah, LDA is generative. Gaussian GMM is generative, so LDA is generative. So we are going to be looking at Bayes optimal classifier works very similarly to your GMM, right? So you want to find that category Y where probability of category given data point is maximized. If you remember, this is exactly what your Gaussian mixture model also did. So it assumes one Gaussian distribution for every category. Then it computes probability of Y given X. The notation here is different, but it's the same thing. Probability of class label given data point. Whichever class label has the highest probability, that is the one you are picking. That's exactly what your GMM did. Now, for that, can we compute this directly? No. So for this, we need these two terms. This again, if you remember, I taught you the Bayes theorem explanation, expansion. P of y given x is P of x given y into P of y. The denominator term we are ignoring. So these two terms are called this term is called the posterior, this is called the likelihood, and this is called the prior respectively. It's the same thing. So I use the notation y. Here they've used the notation ck. But the essential content is the same. Now again, P of x given ck is what we need to find out. But do we know this? No, again, right? As I told you, if you want to know this, again, you need to know mu and sigma. And to know mu and sigma, you need to know this. So that is where the whole problem came about. So far, as far as LDA is concerned, we have not seen anything new. It is all something we are familiar with, right? Is everyone comfortable with LDA so far?
Yes, Akka.
Right. So now, yeah, we want X given CK. So we are going to model our classes as having a normal distribution with mean mu k and covariance sigma. Again, this is the same thing we did in Gaussian mixture model. And this is the PDF of your normal distribution. Again, if you remember, I said probability of data point given class label is your Gaussian PDF. This is the PDF. It's the same thing in my notes. You can go back and look at it. Now, this is where GMM becomes a special case of your LDA. So in GMM, we assumed every class is a Gaussian with its own mean and own covariance matrix, mu A, mu B, sigma B, and so on. So in LDA, we are assuming all the covariance matrices are the same. So in this case, what happens is it can be proved mathematically. Again, that's a lot of linear algebra we are not going into. But when you assume all the Gaussians have the same covariance matrix, what it boils down to is that your decision boundary becomes linear. It becomes a straight line. That's where the L in LDA comes from, right? So basically, what are we doing here? The same story as GMM. Every class is a Gaussian. Every Gaussian has its own mean. The covariance matrix, all classes, all Gaussians have the same covariance matrix. Instead of sigma A, sigma B, sigma C, sigma D, we just have one sigma, right? This is the assumption. So clear so far? Okay. I assume there are no questions. So yeah, this is the same base rule we had. So ignoring the denominator, we can just say this is proportional to this. And because this is a product term, uh, instead of, it becomes easier to handle when you have sums. So we just take log. So your g of x is what we define as the discriminant function. It is log p of x given class plus log p of class. It is the same right hand side term we had in our base expression. We've just taken log and hence it gets converted to summation. Now we wanted to maximize this, right? So whichever class gets maximum value of this, that is the class which I'm going to classify my data point to. So it's the same as maximizing the log. So ultimately what I want to maximize is my gk of x. That is the idea of LDA. So gk of x is this. So this is the same thing. This is the key assumption, Gaussian assumption. So why are we making this assumption that all the Gaussians have the same covariance matrix? It reduces the number of parameters. And we will also see that when you try to find the maximum value of your GK of X, when you go with this assumption, a lot of terms cancel out. So one, things become simple, and two, your line of separation becomes linear. It becomes a straight line. So this is just simple math. You have to substitute your normal distribution ka PDF over here, and you will get some constant terms. You can ignore the constants. And then it is just substituting necessary values into GK of X. The quadratic terms get cancelled out. So finally, you will end up with this expression. So the derivation, it is there's nothing very mathematical about it. Once you understand what is GK and once you know the expression for the Gaussian distribution ka PDF, it is just a matter of substituting, multiplying, expanding, cancelling out, which is why I am not going into it in much detail. You can sit down with pen and paper, work it out. And if you have any questions, please feel free to reach me. So ultimately, when you work it out, this is the expression you'll get for the line of separation. G of x is going to be wk transpose x plus wk naught, where your wk is going to be some sigma inverse into your mean vector, and wk naught is going to be this big expression. So this is your LDA. So if your data looked like this, your LDA is going to project it in such a way that you're able to come up with a line of separation and a particular space in which your points within the same class are mostly closer together and points across classes are kind of far away from each other as much as possible. Of course, there will be one or two exceptions. There's a triangle here, there are a couple of circles here, but overall, LDA does a decently good projection. That's the idea. So is everyone clear with LDA? It's basically the same thing as GMM with that one extra assumption. Any questions? Okay, I assume there are no questions. What do we have pending? We have optimization and regularization pending. You guys want a break or shall I continue? There is not much there. I think I can finish in 30 to 45 minutes maximum, or probably less than that. You want a break or shall I proceed?
Are there any derivations in optimization and regularizer?
Not derivations, but there are like a few formulae which you will have to remember.
Okay,
There's like algorithms, there are some expressions which you'll have to remember, but there's nothing to derive direct.
And
Okay.
these stuff we have to learn, right?
Sorry?
How to get the W1, W0, all that we have to derive, no? That's
In
important,
in
right?
which one?
In the in LDA and all, that derivation was there, no? Applying and then getting
I
GK.
don't think so. As far as I saw these slides, there was no derivation. There was only this canceling part. I'll check the slides again maybe and I'll get back to you. But as far as I went through, this was what was there for LDA.
Okay.
And also apparently for one section the math was taught and for another section they were only told what is what, so there was a disconnect that way also. So if both of you have not been taught the math, I'm assuming it won't be asked, which is why I won't do much of that.
So there was a couple of derivations in SVR and SVM that
So the thing is, okay, I think you guys are confusing mathematical expressions for derivation. This is a question I've been asked a lot by a lot of you. It's not a derivation. If you look at SVM, the thing I taught you like di into wi xi minus w naught, whatever greater than 1, and then you have your Lagrangian primal form, and then you have your expressions for w naught. Those are all mathematical formulae, and you have to remember the formula, you have to put them down, you have to explain what is what. You have to explain this is the constraint, this is the objective function, this is what I'm trying to maximize. Because this is a constraint optimization problem, I'm using Lagrangian. When I use Lagrangian, this is the output I get. You have to write. So I wouldn't call that a derivation, but yeah, a bunch of mathematical statements, yes, and we saw that. Similarly for GMM, you will start by writing the assuming there are two Gaussians, there's this. Now I want probability of y given x. Then you'll write the Bayes theorem expansion. Then from Bayes theorem, you have P of x given by. For that, you have to substitute the Gaussian PDF formula. You'll write that. And for PDF, again, I need mu and sigma. For mu and sigma, I need that x given by whatever again. So it's a deadlock. So we go for EM algorithm. EM, there is one expression for responsibility term. Again, we're not deriving the responsibility here, but that there is a mathematical expression which you will have to write. So yeah, there are not many derivations per se. Maximum likelihood, probably you might get a derivation for univariate case that you've done in statistical analysis. So I didn't want to explain that again. Multivariately, you will not get maximum likelihood mostly, because that's where we come up with the deadlock. That is where we go for EM. So yeah, it's not derivations. It is just formulae and like a bunch of mathematical expressions is how I would put it. Right. Any other questions? Shall I move on to optimizers, regularizers? I assume there are no questions, so I will move on. Okay, we'll start with regularizers first. Are you all able to see the PPT?
Yeah.
Okay, so this is mostly theory, so I will walk through it very quickly. So regularization, I'm sure all of you know, is any modification we make to reduce the generalization error, but not the training error. So the idea is if your model is trained too much on your training data set, then and it has learned too much from there, when it comes to your test data set, it is going to underperform because it is highly tailored to the training data set. So to avoid that kind of problems, we are going to tweak the model in certain ways so that it does not get overfit. That's the idea of regularization. So bias variance trade-off, I'm sure you would have learned in your EDA. So we'll move to the different regularization methods. One thing we can do is, apart from your objective function, you can add a penalty term, some alpha times omega of theta, which is a penalty term. So what happens this way is, um, when your model is trying to, let's say, minimize your loss function, originally it was only trying to minimize this j function. J, let's assume, was your loss function. Now it is trying to minimize j plus alpha omega. So your optimal weights will be different. The optimal weights where this entire thing is minimized will be different. So you can expect your model uh, to be less specific to your training data and somewhat better generalized. That's the idea. Now, this penalty term should be decided based on what your error function is. So if you're using a squared error function, your penalty term will be different. If you're using an absolute error, absolute value kind of error function, then your penalty term will be different, and so on and so forth. That's the idea. That is about how you can play around with the objective function. But there are also certain regularization techniques where we directly play around with the data. So the first thing is data augmentation. So the more data you give your model, the of different kinds, the better it will learn, right? So we have limited data on hand. How do we manufacture more data from that? There are some ways like flipping, color correction, inversion, skewing, stretching, all of that, just to create more data from what you have so that the model is able to learn more. That is your data augmentation. Noise robustness. So the meaning of noise robustness is when a small amount of noise is injected or a small change happens in your inputs, your model should not end up with an exploding change in the output, like a small change of numbers in the input. Instead of giving a 0.01, if I give a 0.1, my output should not blow up unexpectedly, right? So it should be robust to uh, small minute changes to a fair extent. So for that, what we do is we inject some noise into our weights or into our training data's outputs, so that your model, when it's learning itself, it is learning to deal with noise, so it becomes somewhat robust. The next topic is label smoothing. This again is another regularization technique. So let's say you're doing a classification task, your labels are going to be 1000, right? So and then you have some predicted values, let's say 0.5, and the actual value is a 1. Your error is going to be absolute value of the error at that will be 1 minus 0.5 is a 0.5. So accordingly, your weights are going to be updated. Supposing I smoothen these a bit, I make this one a 0.87, and whatever I am removing from here, I added somewhere else. Now the actual output here is 0.87 and the predicted is a 0.5. Then the error is going to be 0.87 minus 0.5, which is a 0.37 if I'm not wrong. So your weights are going to be updated, but not as much as they would be updated in case of a 0.5. So you're not training your model too much for your training data, but you're training it to some extent. That's label smoothing. Noise injection, same thing again. Semi-supervised learning is so supervised learning, we all know, right? You have input output pairs, and then your model predicts some output or it comes up with some output, and then you compare the predicted output versus actual output. You have a loss function. You update your weights based on the loss function, so on and so forth. So in semi-supervised learning, you don't have those pairs. Instead, you give it the input and you make the model learn a representation of the input. When I say representation, I mainly mean it's going to learn some features from the input, some attributes or some important characteristics of the input. Now, using those characteristics, it will later perform some specific tasks. So, It's like initially you just give it some input data, you make it learn the representation, the features. There are no pairs. And then once it has learned the features, you give it input output pairs. It will use these features to build upon that. That semi-supervised learning. Multitask learning is also kind of similar, where you initially train it just with some general data to learn the representation. And then when you're fine tuning it, you will make it perform a variety of tasks so that it does not get very specifically trained towards one task. That is your multitask learning. Early stopping is you choose to stop your training earlier than you decided. Let's say you wanted some 500 epochs, but you feel like after 300 epochs, I'm getting a good enough loss function. If I still continue to train for another 200 epochs, it's going to be an overfit. So I will stop at 300. That is early stopping. I'm going very quickly because these are just theory concepts. There is nothing too complicated to them. But if you have any questions, you can ask me. Any questions so far? No? Okay. Parameter tying and sharing. So you have learned neural networks, right? So you know that between every pair of nodes, we have some connections. Each connection has a weight. So just for one iteration of backprop, there would have been so many weights which you had to update. So in parameter tying, we force a bunch of connections to share the same set of weights. So next semester you will have deep learning and you will learn something called CNN there. Some of you might already know CNN, convolutional neural networks. So there, this concept is primarily, it comes into play. So a bunch of connections use the same weights. So two benefits. One, uh, when I update the set, when I perform the gradient descent or whatever and get the updated set of weights once, I can use that for all the connections where the same weights are applied. So I don't have to do 5 different connection updates, weight updates. That's one thing. Second, because every weight or every connection is not specifically tuned by the loss function, there is some amount of generalization. That's parameter tying and sharing. Sparse representation is when you want to represent your data in very few numbers, as few numbers as possible. Your matrix has a lot of zeros. So what happens is it is forced to only retain the most important features. Everything else becomes a zero. So it cannot retain each and every feature and hence give an extremely specific overfit answer. Sparse representation. Bagging, boosting, and ensemble methods are basically where you have a bunch of different models which take the same data and they do the same task. And finally, we average all of them and give the final output as an aggregation of all the models, because every model has different ways of learning for the same task from the same data. Different things it picks up, different things it does not pick up, different problems it faces, different things it's good at. So when you combine everything together, you sort of one model makes up for the disadvantages of another model, sort of, so to speak. So that is bagging and boosting ensemble methods. Dropout is generally in a neural network, you cut some of the connections. So if your typical neural network which you would have learned in your backprop lessons, every node is connected to every node in the adjacent layer. So in dropout, we just drop some of those connections so that there is learning, but there is not too much learning. That is dropout. And yeah, these are just combinations of that. So those are different ways in which you can reduce your generalization error. Okay, so that is regularization. Any questions so far?
No, Aga.
Okay, just give me 1 minute. Okay, I'll just come back and we'll finish optimization and I'll wrap up. Just 1 second. Yeah, sorry, I am back. So, is the PPT visible? Optimization? Is it visible, guys?
Yes, yes.
Right. Okay. So now we are going to look at different optimization techniques. So when I say optimization techniques, with respect to neural networks, I mean, how can you minimize your loss function or get the optimal weights for the connections, right? So the most common among them is gradient descent. This is what your backprop algorithm works on. So I think you would be familiar with this. Do you want me to teach this or can I skip gradient descent? Okay, I'll assume everyone is comfortable with gradient descent because I was told that you had neural networks for your midsem also. So if you have any questions, you can text me later or give me a call. Stochastic gradient descent is the same thing, but instead of doing gradient descent with your entire data set, you take a small sample and do it with that so that it becomes computationally less expensive. That is SGD. Okay, and then yeah, again, batch and mini batch algorithms are the same. That's your gradient descent versus stochastic gradient descent. Any algorithm which takes your entire data set and uses it for optimization is a batch algorithm. Something which takes a small sample and works on it is a more computationally feasible alternative. That's a mini batch algorithm. So we're going to look at some challenges in optimization. So before we go to that, I'm sure you all know the meaning of minima, maxima, and saddle point in a graph. So now one of the main problems is a local optimum. So when we are trying to, when I say optimization, I am either trying to maximize something such as accuracy, performance, whatever, or I'm trying to minimize something like my error, right? So I want to find the global maxima or global minima. But the problem is sometimes I might end up at a local optimal. So for example, if you take this blue colored graph here, uh, this blue point, the leftmost blue point is the global minimum. Ideally, this is what I want to arrive at. And this one is also good enough, pretty much close, these two. But supposing I'm starting from here and I'm doing some gradient descent, I come here and my gradient descent algorithm tells me you have reached the minimum, then I would assume I've reached the global minimum and I stop here. But it is actually a local minima. I will have to go up a little bit before I can go down. And only then I will reach the actual minima. So local optima is a serious problem and it depends on your initialization, right? In your neural networks and all, your weights are initialized randomly. So if I happen to start by initializing here, I'll either go this way or this way. Either way, I'll be lucky. If I initialize something here, I come here and then I'm going to face a local optima problem. So that is one challenge we face. For local minima. The other thing is plateaus, saddle points, flat regions, everything relates to the local minima problem. So when you have a particular region where your graph looks flat, because we go step by step or incrementally in your gradient descent uh, for a bunch of iterations, if you feel like your graph is going flat, we might assume I've reached the minima or I've reached the end of it. There is no going down beyond this, or there's no going up beyond this. But that might not be the case. It might be a saddle region or it might be a flat region in the graph. So those are things which we can't really predict. The other challenge we face is cliffs and exploding gradients. So if your graph looks something like this, let's say I'm here, this bending point here is my optima. So from here, I come a little bit closer, I come closer, closer, closer. And when I come here, supposing because of my learning rate or for some reason, my after the next iteration, my weights come down to this point, like they jump off the cliff and come down, then it's all going down. I am never going to be able to reach this optimal point. That is what we mean by cliffs. And then we have the problem of exploding and vanishing gradients. Exploding gradient is when your gradient becomes too big that instead of a minute change, the way it's become changed drastically. Vanishing gradient is when your gradient value is so small that there is practically no change. It's a 0.0000 something. So your weights are not updated at all. So these are different issues. Stochastic gradient descent we have seen. So before we move to momentum, any questions so far? No? Okay. So now we are going to look at different techniques or algorithms for optimization. So the first one is going to be momentum. So the idea of momentum is in your typical gradient descent, we only take the gradient of the loss function from this iteration, and based on that we update our weights, right? So instead momentum does an average of past gradient. So it is not just the gradient I obtained in this last iteration, but also from a few past iterations. I take the average of all of that, and proportional to that, I update my weights. How does this help me? Is it keeps me going along the right track. That's the idea. So here's the algorithm. So your yeah, so you have your hyperparameter. So this is the momentum based gradient descent algorithm example. So theta is the weight you're going to update, or the parameter for which we're going to do weight update. And your momentum term is denoted by V, momentum or velocity. The terms are interchangeable. So we have gradient, which is taken as you have the loss function averaged and the gradient of that with respect to theta. This is exactly what you do in your gradient descent in your back prop. It's the same thing. You compute the gradient. Now your momentum is equal to alpha times the existing momentum minus epsilon times the gradient. So what happens here is recursively your gradient keeps getting added to the momentum, right? So initially we already had some momentum. Now in this iteration, whatever gradient I'm getting, that is getting somewhat accumulated in this. Again, next iteration, the next gradient I get, that also gets accumulated. And so multiple previous gradients keep getting accumulated, and theta is equal to theta plus v. So when I'm doing a weight update every time, it is not only considering the present gradient, but also a few past gradients. That is SGD with momentum. So are we clear with that one? Any questions? Okay. Moving to Nestrom momentum, this is again a variant. The only change is that here we do the momentum update twice. Before computing gradient, we do theta is equal to theta plus alpha v. Then gradient, again the same update as we saw in the previous example. And then once again we do the update. This just does the momentum twice. So it is like adding a correction factor. This extra update we do here is just a correction factor to reduce your error. It brings the rate of error down. That's the whole idea of Nestov momentum. So it's just one, what do I say, one modification of your momentum technique. And then parameter initialization strategy. So these slides are not arranged in a, what do I say, a proper sequence. You might not find a flow from one topic to another. So pardon me for that. But yeah, I'm just using the slides I got. So yeah, initialization. So we were talking about local optima, and I told you it depends on initialization, right? So you have to be lucky enough to have initialized at the correct place to end up with the correct optima. That is the whole challenge here. So there is no, how do I say, there's no hard and fast rule. Like if you follow this algorithm, you will start with the right initial weights. But there are certain strategies which are based on achieving certain properties when the network is initialized and so on. So we're not going into those strategies, but we are just being informed here that such strategies exist. Okay. So next thing is large weights. So so when you're initializing, should we go for larger initial values of weights or smaller weights? That's the question. So again, they're not giving us a direct answer saying this is better or that is better. It depends on case to case. If you have larger weights, it's going to your vanishing gradient problem will not be there. Vanishing gradient is when the value being passed is very small that nothing gets transmitted, right? So if your weights are big enough, the chances of that happening are very less. Secondly, uh, the stronger your weights, the to some extent, the more you're going to progress in a single iteration towards the optima. Whereas on the other hand, large weights can result in chaos. The exploding gradient problem is there. That can be mitigated by gradient clipping that is there. So it's like you can set large weights, but if the gradient goes beyond a certain point, I'm going to clip it and I'm going to bring it back to a certain threshold. So that is one sensible way of dealing with the initialization problem. So this is just the same stories. Now, before we go to this last 10 slides, any questions so far? Most of this again is theory only, which is why I have kind of been walking through it quite quickly. Any questions? Okay, I assume there are no questions. So algorithms with adaptive learning rates. Now, learning rate in your gradient descent you would have learned is a hyperparameter, right? It is something we set. So learning rate tells you how much of the gradient I'm going to consider in updating my weights. So we don't take the entire gradient and directly add it to our weights usually. So learning rate, if you have solved an example, your faculty has probably given you a learning rate equals 0.1 or something. So there is so much gradient, but I'm going to take, let's say, 10% of that into consideration and accordingly update my weights or whatever. Now, this learning rate is a hyperparameter, meaning it is the user who decides what that value is going to be. But that also affects your weights, right? So you need to set a good learning rate value if you want your network to get the optimal weights quickly. And there is no way for a user to know this is the best learning rate for this particular neural network. So what we can do is we start with a random learning rate, but the algorithm is or the model or the neural network is going to keep adjusting the learning rate also as it learns. For that, we have different techniques. So the first one is ADAGRAD, which is adaptive gradient or adapting gradient something. So what it does is, uh, again, theta is the parameter for which I am going to I'm going to do weight update. Learning rate eta, this is also going to keep changing dynamically. We'll see how. This delta is a small constant. This is just so that when we perform some division, we should not get a division by zero error. So we'll use this delta in the numerator. So again, you have your samples, you do the forward pass, you compute the gradient. This is the same story. And then you're going to accumulate squared gradient. R is equal to R plus G squared. And then your parameter weight is going to be updated as del theta is equal to minus epsilon divided by delta plus root R into G. So before I go to that expression, let's look at the last expression on the page. Theta is equal to theta plus del theta, right? So this is how we generally update our weights, right? So your new value of weight is equal to existing value of weight plus some changed value. That changed value will be your learning rate times your gradient generally. So here, instead what we are doing is learning rate times gradient divided by some root r, where your root r is square of the gradient. So your learning rate also, it does not just remain 0.1 throughout, but that also varies inversely proportional to the square root of the gradient being accumulated. So if in your, let's say in your first iteration, it is just going to be minus 0.1 g. And then in your second iteration, it will become minus 0.1 divided by something times g and so on and so forth. So as we progress, uh, as we go to greater and greater iterations, lesser and lesser amounts of your gradient are going to be taken into consideration while updating the weights, which makes sense, right? Because when I've done more iterations, I've already updated quite some amount. Now I don't want to do a drastic update and end up on the other side of the optima. So the learning rate is kind of dynamically being reduced. That's the idea of ADAGRAD. Make sense? There are no questions. We'll move on. RMS prop again is similar. All of these are just different ways in which your learning rate is going to keep getting dynamically modified. The only thing that changes is this expression, right? In RMS prop, it is going to be R times rho plus G into G times 1 minus rho, where rho again is a hyperparameter. And these formulae remain the same. Then we have another called Adam. In Adam, we have two such quantities, S and R, both of which are updated in a similar way to your RMS prop. And then your del theta becomes minus epsilon times S upon root R plus delta. So these are just different expressions. There is no particular, what do I say, interpretation behind them. It is just different methods that different people came up with for updating your learning rate, and results suggest that RMS prop and EDAGRAD, all of these have performed fairly robustly, but there is no single best technique. So yeah, with that we come to the conclusion. Any questions, guys? Okay, I will stop recording at this point first of all. So thank you for your time.